So we're going to continue our discussion of power series by sort of expanding what we mean by power series by saying that the power series that I showed you before didn't have this term A in it. And so we're now going to expand it and look at a power series centered at A. So power series centered at A is the same as power series, except it has this minus A here. So instead of just C0 and then C1x, I have C1x minus A. And then instead of C2x squared, I have C2x minus A squared. And now, by the way, is where you can finally start to see why we've been talking about this stuff all this time, which is, if you remember way back to linear approximations, and we talked about linear approximations, and we said that a function f of x is equal to f of a, the function value at some known point, plus f prime of a, the derivative of that point, times x minus a. And so that's your linear approximation. F of x, usually we say, is approximately equal to f of a plus f prime of a, x minus a. That's linear approximation. Go look it up if you forgot it. All right, and I remember I suggested at that time that we could improve the estimate by adding in a term involving the second derivative. And there that is right there, f double prime of a over 2 factorial x minus a squared. And then what we do is we keep on adding terms, and we add, in fact, the nth derivative of a over n factorial times x minus a to the n. Now what they've laid out here in our old textbook is a finite sum with a remainder. But actually we can do better than that. We can write this sum in a more compact way by calling it the sum from k equals 0 to infinity of the kth derivative of the function at the point a over k factorial times x minus a to the kth power. So in terms of the power series, the c0s are this kth derivative of a over k factorial. That's what the cn's are, all right? And so here's the amazing thing about what's called Taylor's theorem. And this is called Taylor's polynomial. So this is Taylor's polynomial, or I guess we call it Taylor's series. This is Taylor's theorem. This is called a Taylor polynomial. That's where we've been headed with all of this. That's been the climax of this. Polynomial. Yes. All right. And here's the cool thing. As long as this series converges, f of x is not approximately equal to this sum. It's exactly equal to the sum, because we're using infinitely many derivatives. So we're looking at the behavior of the function at a point A. We're looking at an infinite amount of information about what the function is doing at the point A. And by doing so, we can know how the function behaves exactly at every point x, at every point in the real line. So that's the power of Taylor's theorem and Taylor polynomial. Of course, to implement it practically, there are all kinds of considerations about, like, I can't really add up infinitely many terms, so how many terms can I add up? And then the other question is, when does it converge and when does it not converge? So that's going to be our next question, is when do these things converge? When do these things not converge? So we're going to start with a specific example, which is sum from n equals 1 to infinity of x minus 3 to the nth power over n. And we're going to ask, for what values of x does the series converge? So this time we're not asking like we were asking before, does the series converge or does the series not converge? This series is going to converge or not converge depending on what x is, and we want to know for what values of x that's going to happen. So the way we're going to find that out is we're going to set up an inequality which starts with the ratio test. So we did all those different types of tests for convergence. The one that's going to be the go-to for power series is going to be the ratio test. It's sort of our most general and most powerful test. So we start the ratio test by setting up, by just examining, I think, the behavior of the term a sub n plus 1 over a sub n. And we really are interested in the limit as n approaches infinity of the absolute value of that, but we'll start by just writing this and try and simplify that out. So we're going to start here, and I'll continue in the next video.